Yeah. Good evening, everyone. So we'll be starting now. So those of you who are not able to join today can always go back and watch the videos later. This will be anyway posted on my YouTube channel, so from there you can definitely watch it later. I'll be sharing my screen now. I hope I am audible to everyone. Can someone please unmute themselves and just concur whether I am audible or not?
Yes, sir.
Yeah. Thanks. All right. Uh, okay. So this week, one second. Let me see whether the recording is on or not. Yeah, it looks like the recording is on. Yeah. Fine. So this week, before anything, let's start with introductions as always. So this course is this is an NPTEL course. Oh yeah, right. Thanks for reminding me. All right, let's go back. Okay, so first let me introduce do the quick introductions. Then we'll go back to the last week's problem and then we'll solve it. So yeah, so this is an NPTEL course. Course name is Basic Electrical Circuits, and the instructor for this course is Dr. Gajendranath Chaudhary. He is from he's a faculty member at IIT Hyderabad. All right, and so myself, I am Mayank Anupam. My name is Mayank Anupam. I am the tutor for this course, so I am currently a PMR scholar, and currently I am pursuing my PhD in electrical engineering at IIT Kanpur. All right, so before starting with this week's content, let's go back and quickly see what we left last week. I didn't solve one question. It is correct. Oh, this was that question, right? So yeah, I told everyone to think about it. So did someone think about it? So we are given this that this network here is a two-port reciprocal network here, right? And we have been given that the if we connect a voltage source here of 5 volts at port 1, we get a current in this direction on the in the second port, right? So with this information and the fact that this is a two-port network, how can we say something about the voltage here when we excite the first port with a current source of 6 milliamperes? Yeah, can we say something about it? Yeah, someone who the person who reminded me of this week's this question. Did you think about it?
No, sir.
So, oh, you didn't think about it, or did you think about it? What is it? Yes or no? Did you
No,
think
no,
about
sir.
it? Okay, all right. So, see, the thing is that in this case, you see, you cannot directly comment about it. Okay, you see, in this case, you know that if you excite with a voltage source at the first port and you observe a current, what is this? This is actually equal to Y21, right? The current in the second port is actually and excitation on the first port. So this is what Y21, right? This whatever you are observing here is Y21. And we know that for a reciprocal network, the relationship is what? Y21 is, what is Y21?
Y12.
Yeah, it is equal to Y12. But what is this in this case? When you excite port 1 with 6 milliampere and you are trying to observe the open circuit voltage at the second port. So this is Z21, right? So is there a direct relationship between Y21 and Z21 for a reciprocal network? So we know that Y matrix is the inverse of Z matrix, right? So let's say the Y matrix is Y11, Y12, Y21, Y22. Moreover, these two, we know that it is definitely, this is a reciprocal network, so this is the condition here, right? Now we know that what is the inverse of this? Tell me. The inverse of this will be Y22 minus Y21, sorry, minus Y21 minus Y21 here, and this will be Y2 Y11, right? And then this will be divided by Y11 Y22 minus
Sir,
Y21 the whole square,
Y12.
right? This is the inverse, right? And this is equal to our Z matrix, Z11, Z21, sorry, Z
Y12, sir.
Z12, Z21 and Z22, right? So let's quickly do this. So what do we want to find out? Z21, right? So let's see whether we can find out Z21 or not. So what is Z21, by the way? Tell me from this. What is Z21? It is minus Y21 divided by Y11 Y22 minus Y21 the whole square, right? Correct? So now tell me something. Uh, we are only given information about Y21, right? And nothing else. So we only know about Y21, and we do not know about Y11 and Y22. So can we say anything about Z21 here? We cannot say. Okay. So if a network is reciprocal, we can only say that the Z matrix and the Y matrix are what? Symmetric, right? They are symmetric. So if the question had been like this, that this is the situation that you are given here. Now tell me what is the current? What is the short circuit current when you do this? So okay, if the question had been like this, if the question had been like this, and find out what is this current I, then you could have solved it easily, because this case, what is this? This is they're asking you about what? Y12, right? In this case, what is being asked to you? The excitation is at port 2 here, what the response is observed at port 1. So this is Y12, right? Since we already know Y21, we can simply say what is Y21. This is fine, but from here we cannot derive any conclusion about this one. Okay, this is not possible. We cannot derive any conclusion. All right. So this is actually not possible. We cannot derive anything, any conclusion. Cannot do and cannot derive, can't derive any conclusion. Is that clear? Is that clear?
Yes,
I
sir.
hope it is. All right. So jumping on to this week's content. Hmm. So what did we see in this week? We learned about what? Op amps, right? So I hope everyone is clear with the basic things about of op amps, basic working of op amps, and so it was covered in pretty much. It was covered in some detail, right? So I think everyone is okay with the content that is taught. So I'm not going to refresh it anymore, because I mean there are a lot of things and already they are covered, and with good illustration, good examples. So I will quickly delve into questions. Okay, so I'll be solving some questions here. Hope you will be able to appreciate them. Okay, Now the first question is, an ideal op amp circuit is shown below with a closed loop voltage gain of AB is equal to 10. Okay, and the range minus 30 volt to 30 volt. If the maximum current in the any resistor is limited to 90 microampere, then R1 and R2 are what? Yeah. So what is this? So between V in to V out, you have a closed loop voltage gain of 10. Okay. So what is the gain between V in to V out? Tell me. What is V out by V in here? What is V out by V in here?
1 plus R1 by
1 plus R1 by R2.
R.
Right? Correct? Yes. And what is this equal to? 10. Right? So what is R1 by R2 equal to? 9. Right? By the way, before doing anything, first always check. The first thing that you should always check is whether the circuit is connected in negative feedback or not. I mean, that is the first thing that you should check. Here, indeed, it is connected in negative feedback, right? How do I say that? Why is it connected in negative feedback here? How do you check whether something is connected in negative feedback or not? So we'll be looking at a problem which asks exactly this question only. But here we can easily say that, you see, if we break it here and if we excite it with a voltage source here, okay, we connect a voltage source, we basically ground this, okay, we short circuit this independent voltage source and we excite it with a voltage source here. The thing which will come in return will be a sign which will that its sign will be actually negative of the excitation. So that is why we can say confidently that it is indeed connected in negative feedback here. All right. So hmm. So tell me. So what? Oh yeah. By the way, now the other information. So R1 R2 can be anything, right? With this, just that you have to maintain a ratio of 9, right? If that condition holds, then you do not need to worry about anything. R1 by R2 can be R1 and R2 can be individually anything. Just have to ensure that R1 by R2 is equal to 9. That's all, right? But now you have been given some other information also. So the output range is minus 30 volt to 30 volt. Okay. So your output V naught, it can go to 30 volt here. Uh, yeah. So it can go to 30 volt here. It can go to a minimum of minus 30 volt here. Okay. So our output range is this much. Okay. Now you have been asked that you have been given other information that the maximum current in any resistor is limited to 90 microamperes. So you see, when V naught is moving up and down, a current is going to flow like this, right? Like this and in the other way also, isn't it? It is going to flow. Now this current is going to flow only through the resistors, right? Now what happens in actual life is that practical scenarios, the resistors have a maximum current rating. Okay, if the current exceeds that maximum value, the resistor can, I mean, resistor operation, a resistor can burn or whatever, the resistor value can change, whatever, and crazy things can happen. In practical scenarios, the resistors that you will be using will have some rating. So this rating is given here. This is 90 microamperes. You cannot exceed this value. The current in the resistors cannot exceed this value. So when do you think is the current through the resistors is going to be maximum? When do you think the current through the resistors is going to be maximum? Tell me. Okay, so the maximum current is going to flow through the resistors when the output is maximum or minimum, isn't it? Is that correct? So what is the maximum value of current? It is V naught upon, so what is I max? Mod is actually equal to V naught max mod upon R1 plus R2, isn't it? This is the maximum current, and it should be less than what? 90 microamperes, correct? So from here, what is the maximum value of V naught? It is 30, right? 30 divided by R1 plus R2 should be less than equal to 90 into 10 to the power minus 6. So from here, what is the value of R1 plus R2? 30 divided by 90 into 10 to the power 6, correct? What will this give me? By 3, right? So it is actually equal to R1 plus R2 should be equal greater than 10 to the power 6 by 3. This is our equation number 2. From equation number 1, we already had a relationship between R1 and R2. So let's replace R1 in terms of R2. So what will this give me? From 1 and 2, what do we get? So R1 in terms of R2 is 9R2, right? So let's write here 9R2 plus R2 should be greater than or equal to 10 power 6 upon 3. So from here we get R2 should be greater than or equal to how much? 10 to the power 5 by 3, which is, and this is ohms, by the way. So this is ohms, this is ohms, this is ohms, this is ohms. This is actually equal to R2 greater than or equal to 100 upon 3, which is 33.3333 kilo ohms, right? And then in that case, what will be R1 then? 33.33 into 9, right? How much will that be? Yeah, options are
100
not there.
kilo.
Yeah, come again.
That
It
would
will
be
be
300
approximately 300 kilo ohms, right? So the first option is correct actually, right? This is the correct option, first one. I mean, yeah, so it should be exactly the answer should have been 33.33 into 9, but I mean that the decimal places are removed here, so this will be approximately the answer, right? Hello, this one is the correct answer, right?
Yes, sir.
Yeah. Oh, actually, by the way, this is not approximately correct. This is actually the correct answer, right? So 10 power 3 by into 9, so it is actually 300 kilo ohms. Yeah, yeah. It's actually the correct answer. There is no approximation here. The correct answer is the first one. So you understand what I did here, and we know this question is very relevant to the practical scenario where you'll have to choose the values of I mean you know you want a certain gain, but that gain can be achieved by any value, any individual value of R1 and R2. In that case, how will you choose what is the value of R1 and R2? So I mean this is one of the flavors of the design problems. Okay, this gives you a flavor of the design problem where you have one only here only one constraint is given, that the current should be less than 90 microampere. In real life scenario, in practical scenarios, when you will be designing, you will be having several more constraints on the values of R1 and R2. From that you have to choose what is the value of R1 and R2. Okay, mm, that's fine. So I don't think there will be any doubt in this question. We're moving on now. Yeah. Hmm. So this question is, find the value of I naught if the input voltage of the circuit shown below is this much. Hmm. So this is the input voltage. Okay, this is equal to 2 sine omega t millivolts, right? And what is this? By the way, this is again, is this in negative feedback? Is this op amp in negative feedback? Is this op amp in negative feedback? Yes, it is, right? It is indeed in negative feedback. So negative feedback is there, so that's not a problem. Okay. What is the gain, by the way, from input to output? What is VO upon VI? What is VO upon VI? It is minus 10, right? Am I right? It is minus 10.
Yes, sir.
Basically, it is 10k upon 1k, which is equal to minus 10. Yes. Now we know what is the gain from input to output. So what is V naught equal to? And yeah, what is V naught equal to in this case? Equal to 10 minus 10 times 22 sine of omega t millivolts, right? This is equal to minus 20 sine omega t millivolts, correct? So this is our V naught at this point. So tell me, what is the current going inside? We have to find out in this question. We have to find out what is this current. Okay, we are trying to find out what is this current. So how will we find out this current? We simply do KCL, right? We find out how much this current is, how much this current is. From there we can find out what is I naught is, correct? So tell me, what is this current? Let's call it I1. What is I1? Is equal to V naught upon 4k, right? So which is equal to minus 5 sine of omega t. What will be this? Microamperes, right? This is I1. And yeah, what is this current? Let's call it I2. What is I2? This is very easy to find out, right? I mean, the current that is going to come from here in this circuit, it is going to move here and then come down here, right? There is no other way to go. So I2 is actually equal to the current which is coming right from this side. So what is this current? This is also I2. And what is I2 here? It is simply VI upon 1k, which is what? 2 sine omega t microamperes, correct? Fine. So I2 is equal to 2 sine omega t microamperes. So we have both the currents, right? So we have this current, we have this current. So what is this current? How will you find out? Use KCL at this node, right? So applying KCL at this node, what is I naught? Is equal to I2 minus, sorry, I1 minus I2, right? What is that?
minus 7 sin omega t
Yes, yes, minus 7 sine of omega t microamperes, correct? So let's see whether that option is there or not. Oh yes, it is. So this is the correct answer, right? So you see, in this case, a lot of current has to be pushed by the op amp, right? See, minus 7 amperes means this current is actually moving this way, in this direction. So how is the current actually going to be? It's actually the current that is going to come here is going to go inside, and the current that is going to come here like this is also going to come inside this. So both the currents are adding, right? And that is totally taken, going to be sunk in by the op amp. So all these questions, by the way, are actually should actually give you a flavor of design. I mean, when you actually design the op amp, you have to be careful of the fact, careful of the application that it is going to be used in. So in the application, if the current, so basically in this case we see that the total current that is going to be taken in by the op amp, small signal current will be this guy here, minus 7 microamperes. This is the maximum current. So while when you will be making your designing your op amp, you have to make sure that it can take in that amount of current, minus 7 microampere. I mean, 7 microampere can be actually taken in by the op amp, that we have to ensure. Is that fine? Yeah, I hope it is fine. This is the answer. So let's move on. Yeah, well, sir. Yeah, in this case, we have to find out what is V naught. Yes. Hmm. For the circuit shown below, find the value of V naught. Yes. First, tell me whether the circuit is connected in negative feedback or not. Whether it is connected in negative feedback or not. Yeah. So how do you check whether it is connected in negative feedback or not? You break something. I mean, there are two op amps here, multiple op amps connected here, right? Between so multiple, there are multiple op amps in the feedback, right? So in that scenario, how do you proceed? How do you proceed to check whether the system is negative feedback or not? Hmm. So in this case, you take them individually. You first, what do? You first, let's say, first let us consider this one. Sorry. First, let us consider this one, and at that moment, let's assume that this op amp is indeed connected in negative feedback, and the two ports are actually shorted like this. I mean, the negative feedback, these two are connected in negative feedback, and these two ports, these two inputs here are virtually shorted. So here, can we actually see that this op amp by itself is actually connected in negative feedback, isn't it? Or can we say that or not? Yes, you can say that, because this is actually connected in negative feedback. So let's assume that the gain is very large and these two inputs are shorted here. Okay. So after that, what do? We break it here and then we apply a test voltage here, right? So let's do that. Let's break it here. Let's apply a test voltage here. V test. So output here will be some gain AV times A naught times V test minus sign, right? This is our voltage here. So what is the voltage here? This is okay. By the way, we have assumed that these two ports are shorted, right? Virtually shorted. So this is minus A naught times V test. So what is this by here? This is also minus A naught times V test, right? When this is minus A naught times V test, what is this? This is also minus A naught times some V test. So in that case, okay, by the way, we will have to short this also, right? We'll have to short this. While doing this, we'll have to short this guy here. There is no need of this voltage source. We have to desensitize all the independent sources. This is shorted. Correct. Now, yeah, yes. So tell me now, if this is minus A naught times V test and this is grounded here, what is the voltage that is going to come here? This is a resistive divider, right? So it will be minus A naught times V test upon 7k into 2, right? So it will be actually 2 by 7. So you see that when we when we apply the test voltage here, okay, we test, we see that the return that is going to come again here is a negative of what we applied, right? We applied a positive voltage here, we test, but we see that the return is negative, correct? So indeed this is actually the right sign for negative feedback, right? So this sign is actually correct. The sign right now, which is this is minus and this is plus, is indeed correct. Correct. So yeah, so let's move on now. Let's so this is okay. So in this case we see that both the op amps are connected indeed in negative feedback, isn't it? Now let's actually do the following. Let's what do we do? So let's solve the question now. So the question is find the value of v naught. So how do we do this? So we know that for an op amp, ideal op amps, in this case since nothing is given, so we will assume this is an ideal op amp. So these two op amps are ideal. So let's call this A2. Let's use different color. This is A2 and this is A1. Okay. So we'll assume. Let's write it here. Assume A1 and A2 are ideal. Okay. So when both are ideal, what is the voltage here? What is the voltage at this node? What is the voltage at this node? We know that both
Zero.
the op amps, yeah, good. Both the op amps are connected in negative feedback, so this voltage has to be what? It has to be ground, right? It should be virtual. I mean, this has to be zero, right? This has to be zero. So this is actually virtually shorted, right? So this is, let's write it with a dotted this thing. That is also shorted. This voltage is actually zero. Uh, okay. All right. Moreover, what can you say about these two lines here? If it is indeed in negative feedback, these two are also shorted, right? So you can as well say that these two are actually shorted, right? These two are shorted, isn't it? Okay. Mm. So by the way, what is the current here? What is the current here? It's 10 volt upon 5k. What is that? 2 milliamperes, right? And where will that current flow? Tell me. How will this current flow?
Two kilo ohm.
This current has nowhere else but to flow through this, right? And from here, from this point, can it go here or it should go here?
4 kilo ohm.
Yes, it cannot move in this direction because there is nothing here. The current entering through to the input of the op amp is zero, right? So it has only one way, where in the 4 kilo ohm, right? This current has to go through this and then it will come here, right? So tell me, if the current is going to follow this route here, what is the voltage V naught in that case? So the current is 2 milliamperes, right? 2 milliampere, which is going to flow through this 2 kilo ohm and then 4 kilo ohm. Tell me what will be the voltages here? So at this point the voltage is minus 4 volts, right? Right. And what is the voltage at this point? What is V naught? 2 milliampere flowing through 4 plus 2, 6 kilo ohms, right? How much will that be? Minus 12 volts, right? Correct. So V naught is actually equal to minus 12 volts. the 2 milliampere current, the current here is, this current here is 2 milliamperes. It is going to flow from right from here, and then it's going to come here. So if you write a KVL here, you will see that the voltage equal to how much? 12, minus 12 volts. Let's see whether that is, yes, that is indeed here. The answer is minus 12 volts. Is there any doubt in this question? I've done nothing. I have simply wrote case KVL here. So voltage at, so V naught is equal to what? So if we write a KVL in this loop like this, so it is actually equal to how much? So we'll start with here. So 10 volts minus the current, the voltage drop across this, right? Which is 5 times 2 milli. So which is actually equal to again 10 volts. So we reach here, which is 0 volt. From here we go in this direction, which is equal to again minus 2 times 2 milliamperes. So 2k and milli cancel each other. This becomes minus 4. From this point, we reach this point. From here we go again in this direction. And what is that? What is the voltage drop here? Is actually equal to minus 4 times 2, right? And that should give me V naught. So this and this cancel each other. So V naught is equal to minus 12 volts. So I hope this is clear, right? This is clear, isn't it? Okay, so no response means everything is clear. Okay, moving on. Yeah. For the circuit shown below, the relationship between V1, V01 and V02 is. So where is V01, V02? Yeah. This is V01, this is V02. So are all the individual op amps connected in negative feedback here? And all the questions that you will be having with op amps, first you have to check whether it is a negative feedback or not. If it is positive feedback, it becomes very easy. You don't have to do anything, because then it is positive feedback. Output will be either output will always saturate. It will always saturate to the supply. So first check whether the negative feedback is satisfied or not. So let's call this A1. This is A2, and this is A3. So this is A1 is connected in negative feedback, right? So it is connected in negative feedback. A2 is also connected in negative feedback. Similarly, A3 is also connected in negative feedback, right? So negative feedback is satisfied for all of them. So this is actually negative feedback. Here also it is negative feedback, and this is also negative feedback. Okay. Yes. Now tell me, what should I do now? The relationship between V01 and V02. So again, since nothing is given, we'll have to assume that. Assume all the op amps are ideal. That is infinite gain. Okay, fine. So if that happens, what is the voltage here? What is the voltage here? This is shorted, right? Virtually shorted. So this is virtually shorted. So voltage at this point at the non-inverting terminal, that is the plus side of the op amp, is Vi. So the same voltage will be appearing here, right? This will also be Vi. Now what? And from this to this, from Vi to, let's call this as Vo. From Vi to Vo, from this voltage to this voltage, what is the gain? It's equal to 3, right? The gain is what? Tell me, what is the gain? Vo by Vi. It's equal to 1 plus 10k upon 5k is equal to 3, right? So if the voltage is Vi here, what is the voltage here? V naught equal to 3 times Vi, correct? Now tell me what will be the condition. If it is 3 Vi here, So it is 3 Vi here also. It's 3 Vi here also. So what is the voltage at this point? And what is V01? It's virtually shorted, right? So it's simply equal to 3 Vi here. Again, if it is Vi here, 3 Vi here, what is the voltage V02 here? This is non-inverting amplifier, right? Sorry, this is inverting amplifier with a gain of -2. So what is V02 here? -6 Vi, isn't it? Are you following me? Are you guys able to follow me? The gain from this point, so the gain from this point here to this point here is how much? -2, right? You see, it's a non-inverting, it's an inverting amplifier. So this is R, this is 2R. So the gain here is -2, right? Gain from here to here is -2. So it's actually equal to, so that is why the input here is -3 Vi. Sorry, input here is 3 Vi. So the output V02 is -6 Vi. Okay. So what is the relationship between V01 and V02? So V01 equal to, or V02 equal to -2 V01, right? So this is the correct answer. Is that fine?
Yes, sir.
Oh, looks like this didn't update. Where is the sixth problem? Oh, 1 second. Let me see, something is wrong here. Okay, I did put the sixth question. Okay, no problem. I think I forgot to put the sixth question here, so let's ignore that. Yeah. So in this question, we have to find the value of V0. Excuse me. Yeah. In this question, we have to find the value of V0. What is the value of V0? Tell me. First of all, whether it is connected negative feedback or not. Yes, it is, right? It is connected in negative feedback, so not a problem. Again, nothing is given, right? So what we'll assume? So we'll assume ideal op amp. Okay. Excuse me. Yeah. So, all right. So this is yeah. So nothing is this. So it is negative feedback, right? And we'll be assuming ideal negative feedback, ideal op amp here. So what is the relationship between voltage at this node and at this node? This is indeed connected negative feedback, and we know that negative feedback, the op amp input terminals, ideal op amps input terminals are virtually shorted, right? So this will be same voltages, right? So, and whatever voltage will appear here, same voltage will appear here, right? So let's, for showing, let's connect them using dashes. Okay, so these are virtually shorted. Okay, so let's call this voltage as V1. So this is also V1. Okay, and now let us solve it. Tell me, how will you solve it?
Current is 4 milliamperes through 3 kilo ohm.
How did you do that?
Uh, After the 3 kilo ohm, there is a 0 volt.
No, no,
And
no, 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 that is not right. You cannot do that. You see, this is not zero. Okay, this is not always zero. This voltage here is not always zero. The only thing that is that we can say about it is these two are virtually shorted. Okay, this here is virtually shorted with this guy. I mean this voltage here. Normally what happens is this is connected to ground, then we say that okay, this is also equal to ground, but that is not the case here, right? This voltage here is not equal to ground. I mean this is not connected to ground, right? There can be a finite voltage V1 here, right? So in that case this voltage will also not be ground. This, I mean, this will not be zero, isn't it? Are you getting my point?
yes,
Yeah, so if you have confusion, so this is very important point. So if you have confusion, I will again explain this. Otherwise tell me whether you have clearly understood this or not. This need not be always equal to zero. This is clear, right? Do you want me to repeat it? Do you want me to repeat it, or this is fine to you? You understood?
fine.
Yeah,
Understood.
all right. So yeah, so we cannot directly, I mean, from here we cannot directly find out, right? So let's write some KVL, KCL things here. So let's do that. Um, so how will I do this? Yes. So write a KVL between from here to uh, from here to this point here. Okay. Let's write KVL here. So what will be KVL? One second. Okay. So my earphones battery is going to be discharged. Okay. Yeah. So write KVL here. What will be the KVL here? Start from this point. So this voltage is 0, right? So 0 minus yeah, this is 0. I mean voltage across this is voltage drop across this is how much? How much is the voltage drop across it? Let's assume some current here, I. Okay, assume some current I. This current is going to be the same here, right? Everywhere. This is also I, this is also I. So this is I, this is I, this is also I, this is also I. So let's, or I1 rather. So tell me what will the case KVL here? So it will be it will be minus I1 times 1k. Okay, voltage is dropping here at this point. So we have reached V1, right? Then then we go left, right, in this direction. What is that? Minus 2I1, 2k I1. Then again we get a voltage rise here, right? This 12 volts here. So it is plus 12 volts. Then again in this direction we get a voltage drop. So what is that? Minus 3k I1, and then we reach V1 again, and then we have a how much? This is V1, right? So this is if we go from V1 to ground, if we go from V1, this voltage is V1, right? We go to ground, then it is actually minus V1 here is equal to 0, right? Or we can also say that this is actually equal to V1. Yeah. So from here what do we get? I1 is common, and minus 1 minus 2 minus 3 is 6 minus 6k plus 12 volt is equal to V1. So what is 12 volt equal to V1 plus 6k times I1, right? This is one relationship that we have. This is equation number 1. We also have another relationship, right? That this node V1 and this are actually the same, right? So what is V1 in terms of I1 here? It is actually equal to V1 equal to minus I1 times 1k, right? So let's replace here. Let's write that here. So what is I1 in that case? I1 is equal to minus V1, or rather, let's replace. This is our equation number 2. So from 1 and 2, what do we get? So 12 volts. We will replace everything in terms of I1, and V1 is equal to minus I1 times 1k plus 6k I1, which will then give me how much? 5k I1, right? So I1 is equal to 12 volt upon 5k, right? So some milliamperes, right? This is our I1. So tell me what is V naught now. Since I have the value of I1 here, sorry, since I have the value of I1 here, right? I can find out what is V naught here, correct? So what is V naught? So V naught is actually equal to V1 times V1 minus 4k times I1, right? What is that equal to? So what is V1 minus I1 times 1k? So minus I1 times 1k minus 4k I1. So this is equal to minus 5k I1. This is equal to how much? Minus 12 volt upon 5k into 5k. This and this go away, so this is actually equal to minus 12 volts, right? So V naught is equal to minus 12 volts. This is the final answer. Do we have that answer somewhere? Yes, we have that. So did you understand what I did here? Did you follow, everyone? I use the relationship. So basically I have this voltage V1 here. We know that these two voltages here, these two are virtually shorted. So basically they are same, right? Because it's an ideal op amp. And negative feedback, the input terminals are virtually shorted here. So that is why I enforce that condition in the second equation. This is the second equation. Okay. No, sorry, I enforce that condition right here in the first equation itself. In the second equation, I simply wrote V1 equal to what? Because of this current that is going to flow, V1 equal to minus I1 times 1k. So from there I got two equations. I got I1. Okay. Now when I have I1, then V naught is easy to find out, right? V naught is equal to this voltage V1 minus 4k I1, right? This is what I wrote. So I hope this is clear to you. Is that fine?
Yes, yes.
Yes. Yeah. So let's move on. So there was also a sixth question, so I forgot to put that there. Ah. Hmm. Yeah. So the question is, if the open loop gain is 10 to the power 5, then the closed loop gain is. So in this particular question, we have an op amp here. Okay. This op amp is now non-ideal. Okay. The gain is not infinity. So in the case when the gain is not infinity, we cannot say that these two nodes here are at same voltage. There can be a voltage difference. There has to be a voltage difference between these two nodes. Okay. So let's find out how much that is. So it is given that the open loop gain is 10 to the power 5. So what is open loop gain? Tell me. So how will you find out open loop gain? You have to break it here. You have to apply test voltage here, V test, and then you have to see how much V return you are getting. Correct? How much V return you are getting. And by the way, at that time you'll have to desensitize this voltage source. You have to connect it to short. Okay. So let's do that. What is V test here? V test I have applied here. So what is this? There is some A naught times V test. Okay. There is some A naught times V test minus A naught times V test. So what is V return here? This minus A naught times. So V return here will be minus 8 naught times V test, and sorry, V return here is equal to minus A naught times V test. Okay, let's write it. V return, which is at this point, is equal to minus A naught times V test into 5k upon 500k, right? So this is basically voltage division, right? So this V naught A naught times V test here, there will be voltage division here, right? So that is what I have written here, 5k upon 495 plus 5k. So 5k upon 495 plus 5k, right? So this is fine. And what is that equal to? 10 to the power 5, right? So what is this? V return is equal to minus A naught times V test upon and 5k divided by 500k, which is equal to minus A naught times V test into 5k upon 500k is what? 10 to the power minus. Yeah. Uh, yeah. And then and what is this? Yeah. So what is loop gain? Open loop gain. Open loop gain is what? It's actually equal to V return upon V test minus V return upon V test, right? So what is this? Minus A naught times V test times 10 to the power minus 2 divided by V test. So how much is that equal to? This will be plus, right? Equal to 10 to the power minus 2 into A naught, right? So this is equal to what? Open loop gain given how much is the open loop gain, by the way? 10 to the power 5, right? So it is 10 to the power 5. This is equal to what? A naught times 10 to the power minus 2. So what is the actual value of A naught? 10 to the power 7, right? Isn't it? The actual value of A naught is 10 to the power 7. Yeah. So from this, now we have to find out. So we have found out the value of A naught. From this, we have to find out what is a closed loop gain, right? So tell me, what is the closed loop gain? So for that, we don't need to do all this. Okay. So for that, we have to replace this op amp by its VCBS equivalent, right? So let's do that. So what is the op amp situation here? This is the op amp given to us. So we have this op amp here. This is 495. Yeah, yes. And we know a naught is equal to 10 to the power 7, right? So what is this equivalent in terms of VCVS? So we have okay, uh, all of you, could you please mute yourself? Yeah, thanks. Yes. Now let's write it in terms of VCVS uh, notation. So this is 5k. Then we have this 495k, correct? And what do we have here? We have this is vi, so this is plus, this is minus, and let's call this v vop. So let's call this vop, op amp. Let's call this vop, or only op amp 1. Let's call this vop 1. And what is this voltage? Is actually right here, it is connected to a VCVS, right? And that this is grounded, okay, and this is our V naught, okay. This is A naught times VOP 1. Fine. So not only what is the voltage here, I mean we know that A naught is equal to 10 to the power 7, right? So let's write it. It's 10 to the power 7 times VOP 1. So now we have to find out what is gain between V out to V in. What is the gain? Closed loop gain, right? We have to find out. Find VO upon VI. So how will you do that? The question is to find VO upon VI. So how will you do that? Very easy, right? Simply assume that this voltage is what? Let's assume that this voltage is this voltage here is, let's call this some V1. Okay, yeah. So now let's write some KCL KVL equations. How will you do that? We'll see what is the current here, right? So very easy. So VO is equal to, or VO minus V1 upon 495 K is equal to V1 minus 5 V1 upon 5K. So that's one equation, right? Yes. And so from here what will you get? So what is V1 from here? So this and this cancel each other. uh, VO upon V1 minus 1 is equal to 495 by 5. So VO is equal to 500 by 5 into V1. So from here V1 equal to 5 5 by 500 times VO. This is our equation number 1. This is our equation number 1. The second equation, what is the second equation? VO, right from here, right? In this relationship, VO is equal to 10 to the power 7 times VOP1. So VO is equal to Second equation is what? VO equals to 10 to the power 7 times VOP 1. And what is VOP 1? 10 to the power 7 times VOP 1 is what? This VI minus V1, right? VI minus V1. So this is VO is equal to 10 to the power 7 times VI minus V1. And how much is that? What is V1 in terms of VO? We already know that, right? So VO is equal to 10 to the power 7 times VI minus V1 is 5 by 500 times VO, right? So let's write it. Let's take VO term here. So VO into 1 plus 10 to the power 7 into 5 divided by 500 hmm, is equal to 10 to the power 7 times VI. So what is VO upon VI? We have 10 to the power 7 divided by 1 plus 10 to the power 7 into 10 to the power minus 2 is actually equal to 10 to the power 5. How much is that? How much is that? This will be slightly less than 100, right? It will be less than 100 to the power 2 because of this one here. There will be only slight variation, right? Only slight change. This will be even greater than 99.9, right? Is that clear? I mean, you see that in the case of a non-ideal op amp, the gain, if the yeah, if this had been ideal case, if this op amp would have been ideal, okay, what would have been the gain from VI to VO? We know that this will be 1 plus 495 upon 5, right? And that is equal to 100, right? That is, but you see that yeah, you see that now since the op amp is non-ideal, right? The gain is not infinity for the op amp. Gain is actually 10 to the power 7, which is very large, but still it is not infinity. You see that in this case, what is the situation here? The gain from input to output, that is closed loop gain, is not actually 100, but is slightly less than 100, right? So this is actually the effect of finite gain of the op amp. You will not get the actual closed loop gain, but you will get slightly less gain than that, isn't it? Okay. Uh, what else? Yeah. By the way, tell me, if the open loop gain is now decreased by 10%, then the change in closed loop gain is, we can see clearly, right? If the open loop gain is decreased by 10%, you can see from here itself that if you write everything in terms of A naught, we see that VO by VI is equal to how much? Uh, A naught divided, so it is A naught divided by 1 plus 10 to the power minus 2 times A naught, right? So if you now decrease the gain by 10%, if you decrease A naught by 10%, you will have some then we will have some further deterioration of the closed loop gain, right? So that you can find out by yourself. In fact, you should do it yourself. You should find out what is the change in closed loop gain if you change the open loop gain by 10%. So just do it as an exercise. Is everything all right with this question? Everything fine? Was this point understood clearly? How did I mean this thing here? How did I find out open loop gain here? You understand what open loop gain is? Everyone, do you understand what open loop gain is? Okay, so no response means everything is fine. So I will simply proceed further. Uh, yeah. Okay, let's first. Yeah, so we have the following question. In the below figure, each op amp has an input offset voltage of 10 millivolts. For offset voltage, yeah. So what is value of V2, VO2? Yeah, see, in this question, we have to learn something about offsets. So what do you understand by offset? See, if you have an ideal op amp, this is, let's say this is minus, this is plus, and we have our terminals here, output, right? So, I mean this op amp here, this is an op amp here. So it has, ideal op amp has infinite gain, and we assume that these two inputs, they are identical, right? We assume that the two inputs to the op amp, these two inputs here, they are identical. They have no problem. They have no mismatch here, right? They have no mismatch here. We assume that the input terminals are identical. So what do I mean by that is, whatever we connect, uh, identical means okay. We assume that if this is V1 here, and if we connect a voltage, another voltage source here, which is, let's say, V2, okay. So what do we assume? We assume that the voltage that is going to appear at the input of the op amp, so this is basically the condition will be how, what is the look inside here. So if these two are the two terminals, then the op amp will look something like this from inside. So this is grounded, and here this will be A naught times V in. And what is V in? This is, and what is V in, by the way? Oh, this is too small to show anything. Let's redraw it slightly. Hmm. Yeah, so we have what inside it, it will be like this, and then there will be a, okay, and this is what A naught times V in. And what is A naught, and what is V in, by the way? This is this is minus, this is plus, V in is this is minus, this is plus, and V in is this one. So we assume that the V in here is equal to V1 minus V2. So we assume, we generally say in an ideal op amp, V in is equal to V1 minus V2. That is what we say, okay, in an ideal op amp. However, in practical op amps, what will happen? Uh, in practical op amps, what will happen? V in will not be equal to V1 minus V2. Okay, so the voltage that will be appearing at the terminals which are outside of the op amp might not be the same as the voltage that is going to appear here inside. Okay, there might be some difference between them, and the way to model it is, this is called offset. Okay, this is called offset problem. This is called offset non-ideality. So this is a big problem, right? this is actually uh, this is a problem of offset. And the way to take care of it is, how do we model it? So mm, let's say v in turns out v in actual v in that is going to appear here is greater than v1 minus v2. Okay, actual v in that is going to appear here is greater than v1 minus v2. So how do we model it here? How do we model it here? We connect a voltage source here, right? Which is okay, so not here but inside it. Oh no, no, not inside it. We model it outside only. Uh, okay, how do we model it? We say that there is a voltage source which is connected here. Uh, and then the terminals are coming out. Then we have this guy here. This is V1. Okay, and this is some V offset here. We call this some V offset here. This is the way that we model it. Now tell me, now tell me what is V in here? V in is equal to how much? Some V offset plus V1 minus V2, right? Right? Understand? So definitely V in is greater than V1 minus V2, right? So we assume that if V in is greater than V1 minus V2, then we say that there is some offset voltage which is going to appear at the non-inverting terminal of the op amp. Let's say V in, now let's say if V in is not greater but V in is less than V1 minus V2. So what will happen to this V offset here? What should I do? I need to simply invert the sign, right? If we write it minus V off, if we simply write V offset is now negative, then this will take care of the modeling, right? Need to go ahead and change the location of this. Oh, sorry. I do not need to go ahead and change the location of this V offset from here to here, right? I can simply add a minus sign to the V offset here. That will take care of the of the inequality, right? So I hope that is fine. So this is the way that we model the op amps which have offsets in them. So that is what is being said here, that in this case each op amp here has a 10 millivolt offset. Okay, so how do you model that? Very easy. Again the same thing. Like in the first case, this op amp has a 10 millivolt offset. How do you do that? How do you deal with that? Between this and this, you connect a 10 millivolt of voltage source like this. So you connect a 10 millivolt voltage source like this. Between this and this terminal, this is 10 millivolts. Okay. Similarly here also, uh, there is a 10 millivolt of voltage source here that you connect. Okay, and then you solve the whole circuit. Then after that you find out what is value of VO2. Is that fine? Is that fine? Okay, so no response means everything is fine. So let's I'll quickly do this. Uh, hmm, okay, so we have the circuit is this one is the circuit we have. Let's see whether I can take a screenshot. Yeah, I can. So, so copied it. Let's put it here. Yes, that's fine. So now let's deal with this. Okay, let's solve this. So I have to find out what is V02, right? This voltage VO2. So let's do that. Uh, okay, so what is the voltage appearing here? Vi plus 10 millivolt, right? That is going to appear at the input of the inverting non-inverting terminal. So what is the voltage that is going to appear here? Since this is in negative feedback, right? Since this is in negative feedback, this is negative feedback, this is also negative feedback, and the gain is infinity. Okay, so what is the voltage that is going to appear here? It's actually equal to Vi plus 10 millivolts, plus 10 millivolts. Okay, similarly if it is 10 millivolts here, so what is the voltage here? 10 millivolts only. Okay, so now that we have written all the voltages, now let's quickly do some things here. By the way, this is very easy. Now what is V01? What is V01? From this point, sorry, or from this point to this point, what is the gain? The gain is 1 plus 100k upon 10k. It's 11, right? The gain is 11, right? So gain is 11 from here to here. The gain is 11. Okay. And what similarly, what is the gain from here to here? Not here to here. Sorry. Here to here. What is the gain? Okay. Let's worry about it later. First, let's find out what is V01. What is V01? It's equal to Vi plus 10 millivolts into 11. Okay, that is fine. Now let's find out what is V02. So this voltage I already know, this is 10 millivolts. Okay, so for V02 we have V01 minus 10 millivolts, right, divided by 10k, that should be equal to 10 millivolts minus V02 divided by 50k, correct? K and k go away, this is 5, right? What is V01? I know already. So V01 and minus 10 millivolts minus 5 by 5 k and k gone. So this is actually 2 millivolts is equal to V02 upon 5, right? So what is this? V01 minus 12 millivolts into 5 is equal to V02. And what is V01? V01 is Vi plus 10 millivolts into 11 is equal to 11 Vi plus 110 millivolts minus 12 millivolts into 5. So how much is that?
Sir, it's
Yeah, come again.
minus V0 2 by 5, sir.
I
In
made a
second.
mistake somewhere.
Minus V0 2 by 5. Second step.
Oh, yes. I'm sorry, yes. Correct. It is minus, yes. Definitely it is minus. Yes, correct. Thank you. Thank you for pointing it out. It's minus, yes. Yeah, so how much is this? 55 Vi, right? And this is, how much is this? 110 minus 12 is 98, right? 98 times 5 is how much? 500 minus 10, right? 490 millivolts. So see the okay, by the way, this is minus sign here, minus sign here. Is that fine? Is that fine?
Yes, sir.
So the actual answer is how much? What is VI?
0.
Oh, VI is 0. So that okay, so whereby, so this is actually V02 is equal to, in that case, 490 millivolts, right? With a plus sign.
Minus.
How come?
Oh, okay, sir. Plus. Oh, plus some.
Just 1 second. I think I missed somewhere something. So this is fine. Minus V02 here. Okay, and then this is minus V02. So I took a minus here.
Positive only, sir.
It is correct, right?
Yes, sir.
No, no. I think I made a mistake here somewhere. This should not be positive. So let's see what mistake I made. I made a mistake here. So let's see what is the mistake here. So this is right, right? This step is fine. This step is fine. At this point, V02 minus V02 is equal to V01 minus 12 volt, which is this guy, into 5. So it should be minus. Yes, there should not have been a minus sign here. I already took the minus sign here, right? This should have been simply minus 490 millivolts. It should actually be minus 490 millivolts. Okay, this is the correct answer. 490 millivolts. Is that fine? See, I already took the minus sign from here to here, right? So I should not have put a minus sign again here. Do you get it?
Yes, sir.
Yes. Oh,
Yes,
okay.
yes.
Yeah. So moving on, problem number 10. Okay, this is too big. Reduce the size of it. Hmm. Yeah, you actually do this on your own. I mean, this is actually pretty easy. You have to first you have to see whether the circuit is in negative feedback or not, and you have to actually check. I mean, you see in this case, you can clearly see in this case that this is actually, you see, there's a feedback around plus side also and minus side also. Okay, so you have to, and you have to see in this case, see the feedback is around plus sign here. So for if you just take a look at it, at the first glance it might look like the circuit is in positive feedback. So actually you should check this, and you should convince yourself that the circuit is in negative feedback. You do this on your own, find the value of I0. I want you to do this on your own. If you are not able to do it, I will inform you in the next session. I will help you. We'll solve it together. Yeah, this question. What is the minimum value of R1 to have dominant negative feedback in the op amp circuit? You see in this question, you see this op amp here has a feedback connection both in the minus side and also in the plus side, right? You remember that if the feedback connection is in the plus side, if there is only one op amp, if the feedback connection is only in the plus side, then that connection is positive feedback, right? That connection is positive feedback. So in a way, this connection here is trying to make it a positive feedback, right? This is trying to make it a positive feedback, correct? Whereas this connection here is trying to put it in the negative feedback direction, right? So which of the two will win? And on that basis only you will be able to say whether the overall circuit is in positive or in negative feedback, based on which of the feedback wins. Okay, so that is why we have the question of what is the minimum value of R1 to have a dominant negative feedback. We want negative feedback to win in this circuit. So how will we make it win? This will definitely depend upon R1. So that is why the question is asking what is the minimum value of R1 so that the overall negative feedback wins. So how do you solve this question? How do you approach this question?
V
Yeah, go.
negative greater than V positive, sir. Taking
V negative greater than V positive. So okay, so I didn't get your point. So tell me, how will you proceed? So this is the circuit. Okay, how will you do this? I mean, yeah, definitely you might be on the right track. Tell me exactly what you are going to do.
sir. Nullifying V in, sir.
Okay, nullify V
Mm,
in first thing. Good. So first thing is definitely nullify V in because this has no purpose here, right? And
yes,
definitely I will short it, right?
yes, sir.
Yes. After that,
At V negative, sir.
at this one, right? What should
Yes,
I
sir.
do?
Yes. R1 by 4. R1 by R1 plus 4 equal to
1 second. Okay. So I didn't quite get it. So let's say this is V negative. Okay. This is V positive. Okay. Then what else?
V negative equal to
Okay. V negative equal to
R1 by R1 plus 4 into
R1
V
by
naught.
R1 plus 4
V
times V
out.
naught.
V out.
How did you get that?
Superpositions. Voltage division.
Hmm. Cool. And what is V positive?
1 by 4 in 1 by 4
1 by
into V
4.
out.
Yes.
1 by 4
Correct.
into V out.
V out. Yes. And what is now?
V negative greater than V positive, sir, for
Yes.
negative feedback.
Yes. Correct. So that's what it is actually. So yeah. So definitely V negative has to be greater than V positive for negative feedback. Yes. Good. Very good. So this is actually correct. So a more systematic way to a more what do I say? A better way to say the same thing that you just explained will be like this. So remember, in all the argument that we just made for negative feedback, we want to make sure that whatever comes, if we apply a test voltage at the input, okay, if we apply a test voltage at the input, if we break the loop, right, and if we apply a test voltage at the input, whatever comes back has to be the direction of that the whatever comes back that has to be it should be in the negative direction of what we applied, right? The excitation should be sorry the response of the loop should always be negative of the excitation, right? That is the whole point of negative feedback. So definitely a different way to say the same thing would be you just break the loop. Sorry. So the loop is like this. So the loop is like this. We have and so this is grounded here. And what else do we have? We also have 1K thing here. And definitely we will be grounding this, right? Shorting it. So Vin is not there, so we will not be using Vin here. So V in sorted, and this is minus, this is plus. From this point we have another, no, we don't have that. Okay, this is 100k, this is 3k, right? This was 4 4, right? 4k. This is R1, this is 1k. Yes, this is 1k. Fine. Yeah, so the whole point of negative feedback is what? If we break the loop somewhere, right? If we break the loop here, we apply an excitation here like this. Let's call it V test. The thing that is going, that comes here, that the return voltage here, V return, should be negative of should have a negative sign, right? So V return by V test should be negative, right? That is the whole point of negative feedback. For negative feedback, right? That is the whole point, correct? So we just have to check that only. We apply a V test here and we see how much is the V return. So what is V naught because of V test? Is actually equal to some A naught times V naught, right? Minus A naught times V naught. That is V naught. That is, okay, so this is A naught times V test. That is V naught, right? The gain of this is A naught, and so what is V naught? V naught is actually equal to A naught times V test, correct? Because of this V naught, what is the voltage that is going to appear here? Let's call it V1, let's call it V2. What is V1? Like our friend just said, V naught is equal, V1 is equal to minus A naught times V test times R1 upon R1 plus 4k, right? And what is V2? Minus A naught times V test into, you see 1k and 100k are in parallel, right? So it doesn't matter, I mean 100k is much greater than 1k, so parallel combination will simply be dominated by this 1k. So it's equal to 1k upon 4k, sorry, 4k. So what is V2? V2 equals minus A naught times V test into divided by 4. So what is V return? So what is V return? V1 minus V2, that is equal to A naught times V test into 1 by 4 minus R1 upon R1 plus 4k, right? And what was our V test? Okay, yeah. So this is V return, right? And what do we want? V return upon V test, which is equal to how much? A naught times, sorry, minus A naught times, oh no, right, only A naught times 1 over 4 minus R1 upon R1 plus 4k has to be less than 0, right? That's all we want, correct? That's all we want for negative feedback. So from this we can clearly get the answer, which will be how much? So it will be R1 plus 4k minus 4R1 has to be less than 0. From this 3R1 has to be greater than 4k. So from this R1 has to be greater than 4k upon 3, which is how much? R1 has to be greater than 1.33k ohms. Got it? So what our friend suggested is also the same thing actually. I just put it more clearly, I mean, just to make sure what is the idea behind doing that. And the answers are not correct here, okay? They are, somehow they neglected this 1k somewhere. They have not ignored the answers have been assumed, they have assumed that 1k is not there, okay? So that is not the case. Definitely 1k is there, so answer will be this divided by 100. So let's ignore this. Answers are actually incorrect here. Correct answer is this. Yeah, is that fine? Is that fine? Yeah, I think it's fine. So let's call it for today. Let's I mean, there was one other problem also, but that's the same kind of problem. This is very clearly to they are simply asking what kind of a feedback is there in this circuit. So this is very similar to the last problem. Just have to break the loop and see whether the return is actually positive or negative. Just have to check that, and you can do this clearly. I mean, if you understood the last problem. So with this, I think let's call it for today. We'll again meet next Saturday, where we'll be discussing some new things. Okay. So thank you for joining. Let's end this session.